Having introduced the concept of stationary states of a quantum particle, I will now discuss some of the key properties to highlight why they are considered both interesting and important. The first property is that stationary states describe physical scenarios where the particle appears motionless. One way to understand this is by considering the probability density of finding the particle at different positions, and recognizing that it is time independent. The probability density is the square of the absolute value of the wave function psi of x and t. By writing psi for a stationary state as the lowercase psi of x, multiplied by the complex exponential function of time, we obtain this expression. Since the absolute value of the complex exponential is 1, the probability density is simply the square of the modulus of psi of x, showing its constancy over time. Another way to confirm the motionless nature of stationary states is by observing the time independence of expectation values of various physical observables. Thus, the expectation value of the particle's position is determined by this integral. Since the squared modulus of the stationary state wave function equals the squared modulus of lowercase psi, it is evident that the expectation value does not change in the course of time. As for the expectation value of the particle's momentum, it is determined by this integral. Let's now replace the stationary state wave function psi with lowercase psi times the complex exponential, and psi star with the complex conjugate of this expression. By exploiting the cancellation of the two complex exponentials, we arrive at this expression for the expectation value of p. It clearly remains constant over time. Following the same reasoning, you can easily see that the expectation values of other observables, such as kinetic, potential, and total energy, also remain constant when the system is in a stationary state. The second property I want to talk about is that stationary states have definite energy. Let's see how we can reach this conclusion. Let's start with the expectation value of the Hamiltonian, which is the energy operator. As with our previous calculations of expectation values, the mean energy is determined by this integral. Note that lowercase psi is the solution to the time-independent Schrödinger equation. This implies that h hat applied to psi equals psi multiplied by the constant e. The constant can then be taken outside the integral, leaving the integrand as the product of psi and psi star, which is the squared modulus of psi. This integral is simply the normalization integral n equals unity. Therefore, we conclude that the mean energy of the particle equals the constant E. To determine the uncertainty in the particle's energy, let's calculate the expectation value of the square of h hat. The calculation proceeds similarly. H hat applied to psi twice equals psi multiplied by e squared, allowing us to factor e squared outside the integral. By replacing the normalization integral with unity, we conclude that the expectation value of the square of the Hamiltonian is simply e squared. Now, the energy uncertainty is determined by the square root of the difference between the mean of h squared and the square of h mean. Since both quantities equal e squared, the energy uncertainty is 0. Let's reflect on our findings. Typically, energy measurements yield random outcomes distributed according to a probability distribution. In the case of a stationary state characterized by a constant E, we've observed that the mean of this distribution equals E. Moreover, we've determined that the distribution has no spread. This implies that in our stationary state scenario, every energy measurement must yield the same outcome, specifically, E. Therefore, there is no uncertainty in the particle's energy value. It is definite and equals E. The last property of stationary states that I want to mention is this. A typical quantum system possesses multiple, or even infinitely many, stationary states, each characterized by its own energy. Importantly, the set of all stationary states of a quantum system is complete. Let me explain what this means. Stationary states of a quantum system are solutions to the corresponding time-independent Schrödinger equation. Suppose we've solved this equation and identified all the linearly independent solutions, labeled as psi sub 1, psi sub 2, and so on. Each of these solutions represents a physically distinct stationary state, characterized by its own energy, E sub 1, E sub 2, etc. Depending on the system, there may be a finite or infinite number of these stationary states. It is a mathematical fact that the set of all stationary states is complete. This means that any state of the system, whether stationary or exhibiting motion, can be expressed as a superposition of stationary states. Proving this mathematical fact goes beyond the scope of this introductory course, but the concept is incredibly powerful and important to understand. Essentially, the property of completeness means that by identifying all independent stationary states of a system and the corresponding energies, one gains access to all possible dynamical states of that system. We will soon use this idea to explore a number of intriguing quantum phenomena.